In this optimization problem, we're finding the largest possible volume of a box with a square base and an open top. The first step in solving this problem is to read through the problem carefully and figure out what information we're given and what we're asked to find. We're told that if 1,200 centimeters squared of material is available to make a box with a square base and an open top, we want to find the largest possible volume of the box. The second step is to fill in each of these four categories using the information from our problem. I went ahead and drew a box with a square base. Now what we have to do is label the sides. If it has a square base, this length and this length can both be X, and then we'll let this height be Y. So let's write down that X is our length and our width. You always want to write down what the variables are. And then Y is our height. Now let's write down our equation. Our equation is going to relate the variables from our diagram to the information that we're given. So let's look back up. In our problem, it says that we have 1,200 centimeters squared of material. So that means the base, the sides, and the top has to equal 1,200 centimeters squared. So let's write down that we have a surface area of 1,200 centimeters squared. And then let's also write down what our surface area is. It's equal to the base, which is x squared. And then it's equal to all four sides, and those four sides are the same, so we're just going to have 4xy. So our equation is going to be x squared plus 4xy is equal to 1,200. We'll leave out the units for right now. Now let's go ahead and find if we are going to maximize or minimize a quantity. Going back up to the problem, it says we are to find the largest possible volume. That means that we're going to maximize the volume. So let's write down what the volume is. The volume of our box is the length times the width times the height. So that is x squared times y. Now we need to put our volume in terms of one variable. So we need to come back to our original equation right here, and we need to solve for y. So let's go ahead and let's do that. We have 4xy is 1,200 minus x squared, and that gives y is equal to 1,200 minus x squared, all divided by 4x. Now let's take that and put it back up into our equation for v. So we have x squared times 1,200 minus x squared, all divided by 4x. Looks like one of the x's is going to cancel. So we end up with 1/4 x times 1,200 minus x squared. Let's go ahead and let's multiply this through. So we have our v is equal to 300x minus 1/4 x cubed. And we are going to need that, so I'm going to go ahead and highlight that. Now let's think about our domain. We are not told how big the length and the width of our box can be, but we do know that it can't be 0 and it can't be negative. So we're going to say that our domain is x is greater than 0, and let's just make a note that this is an open domain. We'll need that in just a few minutes. Our third step is to take the derivative of our volume and find its critical points. I'm going to go ahead and rewrite our equation for our volume. It is 300x minus 1/4 x cubed. Now let's go ahead and let's take the derivative. Our derivative is 300 minus 3/4 x squared, and we're going to set that equal to 0. So we have 300 is equal to 3/4 x squared. If we multiply by 4 and divide by 3, we are going to get, let's see, 1200 divided by 3 is equal to x squared. So this tells us that x squared is 400. And we take the square root of that, and it's really nice. And we get that x is equal to 20. Now we need to put units. Let's go back up. We have centimeters squared for surface area, so x is 20 centimeters. And we'll go ahead and highlight that. Now we need to find y. Our equation for y is right here. So let's use that. Y is equal to 1200 minus x, which is now 20. So we have 20 squared, all divided by 4 times 20. Let's see. This is 1200 minus 400. So this is 800 divided by 80. So we get that y is equal to 10 centimeters. Now what we need to do is find our maximum volume. So let's write down our equation for V. Let's see, we can pick two of them. V is x squared y right here, or the one we have below that. Let's use the x squared y. That one's going to be easier. So V is x squared times y. X is 20, so this is 20 centimeters squared. Y is 10 centimeters. So let's see, this is 400 times 10, so this gives us 4,000 centimeters cubed. Now, it may seem that we're done, but we're not. Our next step is to justify that the answer that we got is a maximum. Our interval is an open interval, so we can use the first derivative test or the second derivative test. Let me go ahead and let's highlight our derivative. There's our derivative right there. That derivative is pretty easy, so I think it's going to be easiest to use the second derivative test. So let's write that down. We're going to use the second derivative test. It would not be wrong to use the first derivative test. It would just be a little bit harder. And let me go ahead and write down here what our first derivative is, so we can then take the second derivative. Let's go ahead and let's find v double prime. It is equal to minus 6 over 4x, which is minus 3/2 x. Now we're going to substitute in that x is equal to 20 centimeters. So we'll say v double prime at 20 is minus 3/2 times 20. And this is minus 30, and it's less than 0. We really don't care what the number is. We just need to know if it's positive or negative. Because it's negative, our function is concave down, and we have a max. We can then say that we have a max at x is equal to 20 centimeters. And then we can also say that v is equal to 4,000 centimeters cubed is a maximum. Now we just have one more step. That step is to reread the problem and then clearly state our final answer in a complete sentence. Let's go back up and look at our problem. Our problem says to find the largest possible volume. So that's what we need to state. So we're going to write down that the largest possible volume is 4,000 centimeters cubed. And that's our final answer.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.